Minimum window substring. Given strings S and T, find the minimum window in S that will contain all the characters in T. Introduction. In string problems, we often need to find a substring that satisfies some condition. One important and popular problem is, given two strings S and T, find the smallest substring in S that contains all characters of T. This is known as the minimum window substring problem. It is an important problem because it teaches sliding window technique, frequency counting, substring optimization, two-pointer approach. This problem is common in coding interviews, competitive programming, string processing tasks. Understanding this problem helps learners improve their knowledge of efficient substring search algorithms. Problem statement. Given two strings. S means the main string, T means the target string. Find the smallest substring of S that contains all characters of T, including duplicates. If no such substring exists, return an empty string. Example, S equals Adobe Code Bank, T equals ABC. Output, bank, because bank is the smallest substring containing A, B, C. What does the problem mean? We need to look inside string S and find a window that contains every required character from T. In simple terms, minimum window substring equals smallest part of S that contains all characters of T. Example concept. Main string means search windows means find smallest valid one. Why this problem is important. A brute force solution would check all possible substrings. That approach is very slow. This problem is important because it teaches how to optimize substring search using two pointers, hash maps, sliding window. Example concept. All substrings means too slow. Sliding window means efficient. Key observation. We do not need to generate every substring. Instead, we can maintain a moving window using two pointers. Left, right. Example concept. Expand window means satisfy condition. Shrink window means minimize size. This is the main idea behind the sliding window solution. Brute force idea. The basic idea is generate all substrings of S. Check whether each contains all characters of T. Return the smallest valid substring. Why brute force is bad. If S is large, the number of substrings becomes huge. Example concept. Many substrings means repeated checking, means high time cost. So, we need a better approach. Optimal approach, sliding window. The best solution uses the sliding window technique. We keep a window inside S and move it dynamically. Main idea. Expand the window by moving right once all required characters are included. Shrink it by moving left. Keep track of the minimum valid window. Example concept. Expand means valid. Shrink means minimum. Data structures used. We usually use a frequency map for T, a frequency map for current window, two pointers, left, right. Example concept. Need map plus current map plus two pointers. Step-by-step logic. Suppose S equals Adobe Code Bank. T equals ABC. Step 1. Count characters of T. We first store how many times each character is needed. Example. A means 1. B means 1. C means 1. Step 2. Expand the right pointer. Move right through S and keep adding characters into the current window. Example concept. A means AD, means ADO, means ADOB, means ADOB. Once all required characters are found, the window becomes valid. Step 3. Shrink from the left. Now try moving left forward to reduce the window size while still keeping it valid. Example concept. Valid window means remove extra chars, means smaller valid window. This helps us find the minimum window. Important condition. The window is valid only when it contains all required characters with correct frequency. For example, if T equals AABC, then window must contain A twice, B once, C once. So duplicates matter. Sliding window workflow. Start with empty window. Move right pointer. Add characters to window. Check if window is valid. If valid, move left pointer. Update minimum answer. Continue until end. Example walkthrough. Let S equals Adobe Codabank. T equals ABC. Window expansion. We move right until we get all characters. Adobe. This window contains A, B, C. So it is valid. Window shrinking. Now move left to remove unnecessary characters. Later, another valid smaller window appears. Bank. This is smaller than previous valid windows. So answer becomes bank Java solution. Import java.util.hashmap. Import java.util.map. Public class. Minimum window substring. Public string min window. String S, string T. If S equals null or T equals null or S.length equals T.length. Map character integer. Target count equals new hashmap. For char C, T.toChar array. Target count put C. Target count.getter default C. 0 plus 1. Map character integer. Window count equals new hashmap. Int required equals target count size. Int formed equals 0. Int left equals 0. Int right equals 0. Int minlen equals integer.max value. Int min left equals 0. While right s.length. Char C equals s.char at right. Window count.put C. Window count.get or default C. 0 plus 1. If target count contains key and window count get C int value equals target count.get C int value formed. While left equal to right and formed equals required. If right minus left plus 1, minlen equals right minus left plus 1, min left equals left. Char left char equals s.char at left. Window count.put left char, window count.get left char minus 1. If target count.contains key left char and window count.get left char.int value, target count.get left char.int value, left plus plus, right plus plus. Return minlen equals integer.max value, true, s substring min left plus minlen. Public static void main string args. Minimum window substring solution equals new minimum window substring. System.println solution min window ADOBCA. Bank, how the code works. Build target frequency map. This stores how many times each character is needed. T equals ABC. Map becomes A equals 1, B equals 1, C equals 1. Expand the window. We move the right pointer and add characters into window count. Example concept. Right moves means window grows. Check validity. When all required characters are matched, the window is valid. We track this using required means total unique characters needed. Formed means how many unique characters currently satisfied. Shrink the window. Once valid, move left forward as much as possible while still keeping the window valid. Example concept. Valid window means shrink, means smallest valid window. Time complexity, frequency map creation, O of T. Sliding window traversal. Each character is visited at most twice. Once by right, once by left. So total complexity is OS plus T. This is very efficient. Space complexity. We store frequency maps. So space complexity is OS plus T in worst case for maps. If only ASCII characters are used, it can be treated as constant size storage. Why sliding window works well. The sliding window works because window expands only when needed. Window shrinks only when valid. No repeated full substring checking. Example concept. Controlled expansion, controlled shrinking equals efficient solution. Common mistakes, ignoring duplicate characters. If T equals AABC, then 1A is not enough. Shrinking too early. Only shrink when the window is already valid. Forgetting to update minimum answer. Whenever a valid smaller window is found, update result. Wrong, formed, logic. Formed increases only when the character frequency exactly matches required frequency. Example concept. Correct frequency matching is very important. Concepts learned from this problem. Understanding this problem helps learners understand. Sliding window technique, frequency map usage, substring optimization, two-pointer traversal, handling duplicate characters. This problem is a very important example of optimized string processing. Simple definition. Minimum window substring. Find the smallest substring in S that contains all characters of T. Final summary. The minimum window substring problem asks us to find the smallest part of string S that contains all characters of string T. A brute force method is too slow, so the best approach is to use a sliding window with frequency maps. We expand the window until it becomes valid, then shrink it to make it as small as possible. This approach gives an efficient solution with O of S plus T time complexity. Understanding this problem is essential for learning sliding window, hash map, and substring optimization techniques.